Good morning and welcome you all for today's class. Today we are going to discuss about vapor compression refrigeration cycle and pH chart, pressure enthalpy chart. How we can use pressure enthalpy chart to solve the problem of the refrigeration cycle, means vapor compression refrigeration cycle. As we know that pH chart or temperature enthalpy diagram chart are useful for solving the problem of vapor compression refrigeration cycle. But in competitive examination, whether it is a GATE examination or Indian Engineering Service examination or Indian Administrative Service examination, if you opt mechanical engineering as our optional subject, then it is almost certain that one question you will always get 20 marks or 40 marks to solve the problem of the vapor compression refrigeration cycle. In this problem, you have to find out coefficient of performance, mass flow rate per minute or cooling effect, tonnage of the system, and also you have to find out dimension of the compressor. Dimension of the compressor cylinder means diameter of the cylinder and stroke length of the cylinder. So all these things you can understand very well today if you follow my lecture today. And first we vary of thermodynamic relationship to solve the problem. You have to find out coefficient of performance. But by using this data, you must know how this data can be visualized on pH chart, pressure enthalpy chart. This is very, very important. Otherwise, because vapor compression cycle work in closed cycle, and each process, whether it is a compression process, condensation process, expansion, isenthalpic expansion process, or evaporation process, that is a cooling effect produced in evaporator. So all four processes you can see on the pH chart, and then you can solve this question by taking data from the pH chart. That's why first I will explain how various properties are defined on pH chart, and then we draw cycle and various situations, what type of question may be asked, what type of equation we will use, and then we also solve question for each type of question. So first we will explain pH chart, and this is a pH chart, and here enthalpy in kilojoule per kg, and you know that enthalpy is H equal to Cp into T. So temperature line will also along the x-axis, and this is the y-axis, and pressure is represented by bar, and this is the condenser pressure PC, and this is a evaporator pressure PE. So we know that refrigeration cycle works in closed cycle. Suppose it is starting here, so we have to extend pressure line here. Let us draw entropy lines also. So first we draw entropy lines, because compression process is a isentropic process. So this is isentropic process. These are entropy lines. And we have to draw also some constant volume lines, means specific volume lines like this. These are specific volume lines, and correspondingly these are also temperature line. We have to draw temperature lines. So first we draw a process in which this is a CP, critical point, and from critical point to right, it is a totally vapor line, gaseous state, and this is a liquid state. This one is a liquid state, and from evaporator, vapor enters. Let us draw cycle of the evaporator, taking this one. So along this axis, because it is a constant entropy lines, isentropic process, so process will be like this, and this is a constant enthalpy, and this is a one process. I have defined 1, 2, 2 dash 3 and 4. So 1, 2, 3 and 4, and accordingly here you have to show temperature lines. Let us define temperature lines. This is a given temperature line T1, and T2 dash. Here you will find superheated region T2, T2 dash and T1. So if you move right direction along x-axis, temperature will increase. And there are so many temperature lines here. You can show this is temperature line, and so I have given all temperature lines that are required for solving the problem. So you see that 1 to 2, 1 to 2, and the vapor enters into compressor at fully saturated state, means fully in vapor state, and after compression it leaves the compressor at superheated state from, and then it comes to condenser. At this one, first cooling will take place at constant temperature. Here temperature is constant because temperature remains constant from 2 dash to 3, but here temperature is decreasing. 2 to 2 dash temperature is decreasing, then temperature remains constant. At constant temperature and pressure, condensation will take place, heat will be removed, and from 3 to 4, it is a isenthalpic expansion process in expansion valve. So temperature, you can see temperature and pressure both will decrease. Temperature and pressure both will decrease, and then it will start. Here it is in liquid state, low pressure, low temperature. It will enter into the evaporator, and heat will take from surrounding of the evaporator. Some in a space, some commodities will be there. Heat will be taken from that space, and this is a cooling effect process. Cooling will take place in process 4 to 1. And in solving the problem, for example, capacity is given Q. Q is given some 10 ton, 10 ton. This is a tonnage capacity that is defined of the system. System's capacity, how much capacity of system is there to, that is how much cooling can be produced in that system. So what is the cooling effect Q? That is H1 minus H4, and compressor work will be H2 minus H1, and COP can be defined. COP you can define as cooling effect upon work done, and cooling effect is equal to H1 minus H4 upon H2 minus H1. And you see that in table, what are values that are given in the table. You will always find table, because for given temperature and pressure, you will know H3, you will know H1, you know H2 dash. All these 4 values you will find that are given in the table. So only these values you will get, and you will also get CPG in this region. You will also get CPG in this region. CPG, because here vapor is in gaseous state, in superheated state. So 2 dash means जो ये gaseous state है, यहाँ से from this point to this point, what is the specific heat of the refrigerant, that will be given in the question. You will always find this value given in the question, that will be in table. So you will find how you will get H2. So you know that this process H1 to H2 is a isentropic process. This is a isentropic process. H1 to H2 is a isentropic, because you know that this process is taking place along the constant entropy line. This is entropy lines. These are entropy lines, constant entropy lines. So by using this property, S1 equal to S2. S1 equal to S2. That is equal to. Now S2 equal to S2G. S2 equal to S2G. This formula we will use, because at this point entropy will be given in the table. You will always find entropy at this point, S2G plus CPG natural log T2 upon T2 dash. T2 dash or T2G. Now in this equation you find that S1 is given. S1 equal to S2. S1 will be given in the table. S2G is given in the table. CPG will be given in the data. Only unknown is T2. And T2G, this temperature will be given. These are given things. From this equation you can find out T2. Now T2 you know. From using this equation, if it is thermodynamic equation, very simple equation, and you have to remember, if you don't remember, you see that this is a dimensionally correct. This one is a dimensionless number, this whole value is dimensionless number, and this kilojoule per kg Kelvin, kilojoule per kg Kelvin. So if you find any doubt in remembering this equation, then use dimensional homogeneity. So this equation you can use for finding out temperature T2. Once you know temperature T2, the rest of things are easier. Now you can find out S2. S2 equal to S2G plus CPG and T2 minus T2G. Everything is known. S2G is given in the table. S2G enthalpy at this point will be given in the table. This value is already given. This temperature is already given. T2 you have calculated just by using this equation. So you can find out H2. Now you can find out H2. Now by using these values, now you can use these values. So you now use these values. So you have to find out now here H2. So COP equal to COP equal to H1 minus H4 upon H2 minus H1. This is a very simple equation because already a known quantity that you have calculated by using equation H2. Rest of things are already given. So sir, for finding out H2 we have used different equations. So by using now you know H3 equal to H4. H3 equal to H4. H4 equal to H3 because process 3 to 4 is a isenthalpic expansion process in an expansion valve. That is a throttling valve, or you can say capillary tube. Inside capillary tube, this isenthalpic expansion process takes place in refrigerator or refrigeration system. So now it is known. Other things you have to find out what is the mass flow rate because tonnage is given Q. So suppose Q equal to M into cooling effect QE equal to M into cooling effect H1 minus H4. Then suppose given 10 ton. So 10 ton means 3.51. 1 ton of cooling effect equal to 3.51 kilojoule per second or 210 kilojoule per minute are equal to 12,400 kilojoule per day. That is a unit. Any unit you can use. 1 ton equal to that is 1 ton equal to either 3.51 kilojoule per second or 210 kilojoule per minute or 12,400 kilojoule per day. Day means 24 hours. So here we are using 3.51 kilojoule per second equal to QE. Q equal to H1 minus H4 into M. So mass flow rate of the refrigerant equal to 10 into 3.51 upon H1 minus H4. So from here you can find out mass flow rate. Next what you have to calculate, this is the mass flow rate. You can find out what is the theoretical power of the compressor. So power of the compressor you can find by P equal to M into, this is a mass flow rate. We have used kilojoule per second. So directly you can put here this value M into H2 minus H1. That power will be in kilowatt because this value kilojoule per second and this value kilojoule per second. So you will get kilojoule per second. So kilowatt. So power you will get in kilowatt. And another thing that you might have to ask to find out dimension of the compressor. For example, here we take here dimension because already we have calculated, and at this point you know either from the table data will be given at point 1 what is the specific volume, because the specific volume are passing here. Yellow lines are specific volume lines. So specific volume you can find from because data will be given in the table. At this point data will be given. Suppose at this point you have to calculate it. So mass flow rate, specific volume is known. Specific volume is known for you, which given specific volume, that is a meter cube per kg, that is specific volume given, and so what will be actual volume that will enter inside the compressor at this point. So V equal to m into specific volume. From this equation, you can find specific volume, sorry, actual volume that compressor has to handle. Now, if compressor is given, suppose n is given 1200 rpm, 1200 rpm, and length of stroke is given 1.2d. That's generally given in the question. D, diameter of the cylinder, and 3 cylinder. Compressor has 3 cylinders and 4 stroke. So we volume handled by each cylinder, because if there are 3 cylinder in compressor, then volume will be equally distributed into 3 cylinders. Actual volume handled by one cylinder equal to V by 3. V by 3 equal to pi by 4 into d square. This is area of the, suppose this is a cylinder and this is a piston and this is a stroke maximum displacement. This is a maximum displacement takes from here to here, stroke length, and this is a diameter of the cylinder. So this is a cylinder maximum, this is stroke length L, and so L means 1.2d given, and into how many revolution takes place in 1 minute, that is equal to 1200 multiply 1200, and then you can find out diameter of the cylinder. So diameter of the cylinder equal to d cube equal to V by 3 into 4 upon pi into 1.2 into 1200, that is d cube. So d equal to 4v upon 3 pi into 1.2 into 1200 power 1 by 3. From here you can find out the diameter of the cylinder, and then L equal to length of stroke length 1.2d. So these are the questions that we have to use for solving problem. So almost all calculation that required, that may be asked in question, I have mentioned here, and what are situation in which question can be asked. So what are different situations that we are going to discuss here? These are constant pressure lines, PC, P condenser and P evaporator. There will be corresponding temperature lines also here, T1 and here T2. So various situation will be there. Let us the water situation. Either compression will take place from here. State 1, condition 1, 2, 3 and 4. Condition 1 means after evaporation, vapor enters compressor at fully saturation stage and reaching after compression in superheated region. Just I have solved this question, and now this is a 2G. A gaseous state. So that is a cycle. This is just one cycle, and there is undercooling also. Take some undercooling, 3 dash and 4 dash. Suppose the undercooling is also. After condensation, further cooling takes place. So here further reduction in enthalpy. Second stage may be vapor enters into the condenser at some this condition and reaching. This is a condition. Second condition, 1 dash UG means there is a mixture of the vapor, mixture of the refrigerant. This is quality of the refrigerant having some moisture content, and after compression it is just a saturation stage, just a vapor, saturated vapor. After compression, refrigerant becomes fully saturated. This is state, this is another condition, and further undercooling takes place. Are you reach up to this point? Third condition is before this is most important, because this one is almost impossible to achieve. This condition also almost impossible to achieve, because how evaporator can be controlled so that after evaporation vapor is just fully saturated, no moisture content and no superheat. This is also impossible, and this point is also very difficult to achieve, because compression will start at this point in such a way that after compression vapor will be, when refrigerant will leave the compressor, it is fully saturated state, means fully gaseous state, no moisture content and no superheat. So this point is also very difficult. So for practical operations operating system, there is little bit superheating will be there. We take some superheat. Some 5 to 10 degrees superheat is required to operate this one properly. So we will take here some superheat, and this is a actual practical process. This is a 2 dash, 1 double dash, 2 dash and 3 and 4. So for actual practical operation of the refrigerator, before entering into the compressor, little bit superheating of the evaporator, refrigerant takes place inside evaporator using either there is a heavy pressure, heavy load of the evaporator, or taking condenser heat that is released from condenser to make it superheated. So this is the ideal condition, and most of the questions you will find from one double, this is ideal condition. So all three conditions, and to increase the cooling effect to be further subcooled here 5 to 10 degrees centigrade, 5 to 10 degrees centigrade, so that here cooling effect H1 dash minus H4 dash, that is increased cooling effect. In that case you will see that increased cooling effect, and there is a little bit increase in compressor work, but this is not as much as we are getting gain in cooling effect in this process. That's why this is a most practical and most advantageous process of the refrigeration. So all three cases we will discuss how we find this quality here, then calculate H1 dash, how we find H1 double dash and H2 double dash. All these things we will discuss in next class. So my purpose of discussion is that you know all properties which is required for the calculation of the cycle and solving the problem of the refrigeration. So already we have defined all equations. So we come in next class with a numerical question and solve all three cases by solving all three cases. Thank you very much for watching. Wish you happy day.